Okay, this is basically refers to energy can neither be created nor destroyed during a process. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're gonna continue with a new chapter. We're gonna discuss on heat transfer. In this chapter, you're gonna deal with basic science on the rate of transfer of thermal energy. Okay, the chapter is quite an introductory, which is the first course that you're gonna learn in thermal engineering. Okay, the objectives of this chapter, you're gonna learn on the basic principles of heat transfer, understanding on how heat transfer mechanism works, using some real examples, and how to calculate them. And in the end, you're gonna able to develop intuitive understanding of heat transfer and their relevant concepts. This chapter is important because in practice, understanding the mechanisms are crucial since heat transfer is everywhere in your everyday lives, not only for engineering work such as in designing vehicles, power plants, electronic devices, refrigerators, buildings, and among other things. But it happens such as when you cook, when you seek for thermal comfort during winter and summer. For example, we are putting heavy coats to insulate our bodies in winter and wear less of them during summer. And we also try to minimize heat gain by staying in shades, drying up your clothes under the sun. And when we have a bonfire where everybody gathered around it to get some heat. So in general, we actually practice the concepts of heat transfer whether we realize it or not. We start this chapter with some definitions, a review on thermodynamic laws that form the framework of heat transfer, and we're going to discuss in brief what are the differences between thermodynamics and heat transfer, and finally we present to you the mechanism of heat transfer itself. As engineers, we are often interested in the rate of heat transfer, which is the topic of the science of heat transfer. Okay, before we start, let me explain about energy. Energy can exist in numerous forms, such as thermal, mechanical, kinetic, potential, and etc. So what we're going to deal with today is actually heat. It is a form of energy. We have lots, right? But for this chapter, we're going to concern only on heat, and specifically the heat transfer, how heat is transferred. Okay, so what is heat transfer? By definition, in brief, it is actually an exchange of thermal energy due to the difference in temperature. That is heat transfer. Okay, there are two keywords here. The first one, exchange of thermal energy. So we are only concerned on the thermal energy from state number 1 to state number 2. Okay, like I mentioned previously, energy can be, we have lots of form of energy. We have work, okay, we have kinetic, potential, okay, but here there is change of state, state 1 and state 2, but only concern on heat, okay. And the second keyword is the difference in temperature, okay. Temperature difference must exist. Without this, heat cannot transfer. You can find some other form of definition for heat transfer, but what I put here is in brief, and what is the key that should be available in the definition. Okay, now let's see some example. Imagine you have a rod. At one end of the rod, you light up a fire, and you held the rod on the other end. It means your hand is there, your bare hand. Okay, the temperature of the rod that is light up by fire, let's say 80 degrees C. Meanwhile, the tip of the rod that we held is 29 degrees C. Okay, let's assume that the rod is made of steel. Okay, now here we have the conditions that allow heat to transfer. We have two different thermal energies at different positions, and we also have temperature difference. So basically, you know what's gonna happen, right? I mean, heat transfer is happen in our lives every day, okay? So by experience, what's gonna happen? Eventually, heat is going to transfer from high temperature side to low temperature side. So what happens is the low temperature will rise up and it becomes hotter. What is the temperature is gonna be? We don't know. It depends. If the fire is hot enough, maybe it rises up until 80 degrees C as well. So if both is 80 degrees C, now in this condition, heat transfer will stop because there is no temperature difference anymore. We call this as equilibrium, thermal equilibrium, when both temperature are the same. Okay, so what else? Let's see another example. Okay, now imagine you have a room. The temperature inside the room is room temperature. So what is room temperature? Perhaps we assume, let's say 29 degrees C. Inside the room there is a table. On top of the table, we put a coffee. Okay, that coffee is hot. Okay, let's assume the temperature of the coffee is 70 degrees C. Now again, right? This condition also fulfill the factors that allow heat to transfer. We have temperature difference, which represent two thermal energies. So there will be an exchange of thermal energy. So what happens is, after some time, the temperature of the hot coffee just now will go down, and if it is long enough, it becomes similar to the room temperature. Okay, so these are the two examples that I gave you. Okay, so we As engineer, we try to use this concept to apply it to engineering devices such as heat exchangers, refrigeration process, refrigerators, air conditioning, okay, the concept of heat transfer. So now I allow you perhaps 5 minutes to think what are the other examples or conditions that you can relate to heat transfer. Okay, so these two examples that I gave you is actually have different mechanism of heat transfer. It is important to determine the mechanism because we want to apply correct equations in order for us to calculate the rate of heat transfer or any other information that we can calculate from the equation. Okay, we need to discuss a little on laws of thermodynamics because the laws form the concept of heat transfer. Okay, we're gonna discuss two laws of thermodynamics here. Okay, the first law of thermodynamics, also known as the conservation of energy principle. By definition, first law of thermodynamics is rate of energy transfer into a system is equals to the rate of increase of energy in the system. Okay, this is basically refers to energy can neither be created nor destroyed during a process. It can only change in forms. Okay, so let's say if you have 10 kilojoule of energy. Okay, so that 10 kilojoule of energy is in the form of work, for example. Those 10 kilojoule of energy cannot be destroyed. Okay, it can only change in form. Okay, this 10 kilojoule cannot be simply become 8. Okay, it can become 8, but another 2 may be in this state now become heat, for example. Okay, so 2 plus 8 in total still 10. Okay, so that is the first law of thermodynamics. Okay, so take a look at the equation. We have Q equals to delta U plus W. So this equation basically governs all energy. Okay, we have Q thermal and delta U is internal energy and W is work. So if there is any change of delta U, for example, there will be a change of W in order to sustain the amount of Q, right? So what is internal energy? It is actually the forms of energy related to the molecular structure of a system and the degree of the molecular activity, which are referred to as the microscopic energy. Okay. So the sum of all this microscopic energy forms the energy that we call as internal energy. Any substance have their own pressure and temperature. Okay, so when you have a pressure and temperature, okay, we can find the amount of internal energy. For example, if you have a medium A is at high pressure and high temperature. So since you have high pressure and high temperature, the degree of molecular activity, we're talking about whether it is actually high activity or low activity. So in this case, it's going to be high since we have high pressure and high temperature. And how about the molecular structure of medium A? Maybe medium A is gaseous. So the molecule is very far away. So these two things is actually forms what we call as internal energy. Meanwhile, we have medium B, which is at low pressure and low temperature, and it's actually made of solid for example. So solid is the molecular structure is bond together, right? Okay, and medium B is actually at low temperature perhaps. So the molecular activity for medium B is low. Okay, so the internal energy may be less compared to medium A. So that is internal energy. How about work? Work is in the form of there is an existence of compressor and turbines. Okay, basically you can calculate the work of a turbine. How much work is given to a turbine to move, and how much work is supplied by a pump to a system. So that is work. So these two things have their own pressure, have their own temperature, so and heat. Okay, so the total amount should be the same. Okay, the only difference is, let's say if now you have higher work, for example, the pump is rotate faster. Okay, it means higher work. So that energy must come from something. Okay, it cannot simply just happens. Okay, it must come from the change from something. Okay, maybe the potential energy. Okay, maybe the kinetic energy or electrical energy, right? So that's how energy works. It cannot be destroyed, and in fact it also cannot be generated. Okay, energy is always there but change in form. So who created energy in the first place? Okay, so that's the question, and I believe you know the answer. Okay, next we go to second law of thermodynamics. So what is second law of thermodynamics? Second law of thermodynamics stated heat is transferred in the direction of decreasing temperature. Okay, you have high energetic particles, which is high in temperature, and low energetic particles, which is low in temperature. So heat will transfer from high energetic particles to low energetic particles. Like what we discussed just now in our example. Okay, we have a cup of coffee, hot cup of coffee, and in the end eventually it the temperature will go down. Okay, in the direction of decreasing temperature. The same like steel rod just now. Okay, you have heat transfer from higher temperature to lower temperature. So that's why the tip of the rod that you held, the temperature is rise up. Okay, now we discuss on what is the difference between thermodynamics and heat transfer. There are two main differences. Okay, thermodynamics deals with amount, the total amount. What is the amount of heat transfer as a system undergoes a process from one equilibrium state to another equilibrium state? For example, just now we have internal energy is 10 kilojoule, and that internal energy, two of them become work, right? So that is thermodynamics, the amount, the total amount of energy. How about heat transfer? Heat transfer deals with how fast is from that 10 kilojoule of internal energy, it becomes 2 kilojoule of work, right? So how fast it takes, it becomes 2 kilojoule. Okay, is it gonna take 1 hour? Is it a day? Is it a week? Alright, so we deals with how fast or how long, basically what we call as rate of energy transfer. So in our case, since we deals with heat in this chapter, we are actually talking about what is the rate of heat transfer. Okay, how long does it take to transfer heat? So now you know what is the difference. So the other difference is actually the unit. Okay, for thermodynamics, we always talk about joule. Okay, that is the unit of energy. Normally we put as kilojoule, but in heat transfer it's actually joule per second, right? Per second, meaning rate of heat transfer. So instead of joule per second, we normally put it as watt. So these are the two main differences between thermodynamics and heat transfer. Okay, so let's write it down. Thermodynamics is amount and the unit is joule, or sometimes they put it as kilojoule. So heat transfer deals with how long or rate of heat transfer, and the unit is joule per second. Joule per second is watt, right?